Okay, sorry.
Tell me where the blind spots are. I'll go for it. You guys have your digest?
Yeah.
All right. So let's start out in section 16. I'm going to cover this really quick since I got maybe an hour, and I got to cover our whole gamut, okay? But on like 16-2 is what we call a manual starter. And all that is a manual device to turn on or off a motor. People use it for like exhaust fans, you know, in commercial jobs for bathrooms, you know, anything that can be manually controlled that doesn't need some type of remote control. Do you need another one? Oh, okay. And there's a difference. There's a motor starter, and then there's a manual switch. Okay. The manual starter actually has a place to put an overload into, and what an overload does is we size the overload depending on the size of the motor. So we know, you know, if the full load amps the motor is 1.4, we put in the proper overloads so that, you know, if the motor exceeds that current for more than 20 seconds, it'll trip it basically out. Some small motors are self-protected. They got the little reset button on them. In that case, you don't need a starter. You can just use a switch. But that's the only difference between those two devices. And it's strictly manual. Now, when you go to magnetic starter, the difference with this product is it's got a coil on it that energizes, you know, the contacts inside. And where we use that is if you need some type of remote control, like a building automation system or something like that, controlling a fan, you know, where they want to be able to tell when they want that fan to run and when they don't, okay? In that application, you would need what's called magnetic starter, and our NEMA type magnetic starter are probably, well, they're on page 16-21. And probably prior to that too, 16-18. So I think 21 actually shows a picture of our NEMA type starter. Again, the top part's the contactor, the bottom part's the overload. And all the overload does is it's there to protect the motor. So if the motor pulls more current than it's rated for, it will take the starter out, trip it out. So you haven't covered any control stuff yet, right? 2-wire control, 3-wire control, that type of stuff. I think we need to get into that type of detail.
No, they wire the magnetic starter, you guys will get it, right? So they're familiar with the,
okay, so you're
the
familiar
magnetic
with
starter and the coil and the power circuit.
2-wire control is basically like a maintain device, like a selector switch. Okay, it's on or it's off. You turn it on, it's going to run. You lose power, power comes back on, it's going to run again. Okay, and some installations like conveyors or mixers or something like that, that may not be a good situation, right? Because the power goes out, what's the first thing somebody does? They start digging in, find out what's wrong. All of a sudden, power comes back on, the guy's munched. Not good. So with 3-wire control, we actually use, and the reason they call it 3-wire control, oops, well, let's see if I can do this. I can't. So we got basically here's your coil, and then here's your overload. Okay, so in 3-wire control, we have a start. Wow, I just really suck at this. You didn't record that, did you?
Don't worry, another do.
Okay, and then what we do is we actually use. Okay, this is a stop. Oops. Dang it! I gotta erase this. I did that wrong spot. I'm getting old. Okay. Now I gotta put it back for it to work. All right. So basically, here's our stop button, and around this part, we actually use what we call closing coil, okay? So you push the button down, it completes the circuit, the coil closes, okay? So we use an aux contact off that coil. So as soon as that closes, this closes. Now when you release the start button, now the circuit bypasses it and it runs, okay? You lose power, the coil drops out, this opens back up. Now when the power comes back on, the system will automatically start up. And that's kind of when we use that type of control circuit, is when, you know, either it's not safe, you know, to use a two-wire control. That's when we go to a three-wire type control system, use a momentary push buttons. The other place we use two-wire control is maybe on a remote lift station or something like that that's 20 miles away, and every time power goes out, it's going to drive 20 miles, start it and back out. That's not a good situation. So we'll use two-wire control to maintain control at that point. That's just kind of generic. You didn't want me to erase this stuff, did you? No. I'll just see if I can rewrite. It's a good thing that I'm not an artist. So there's a control portion, and then as far as control power, there's three different types of control power. One's called common control, where we actually get the control voltage off the line voltage that the starter is running on. One's called separate control, where we may take control power for that starter from a panel board somewhere else, bring it in. And the only thing that you have to worry about that is, you know, when the disconnect is turned off, everything in that enclosure has to turn off. So what we normally use is like an auxiliary contact off the disconnect to also disconnect the control power when we disconnect the main power to that product. And then control power transformers. So I just want to cover the basics on starters. You got, you know, different types of control, two-wire, three-wire. You got different types of control power, separate, common, or CPTs. And then to keep going back, we just kind of covered the standard starter, which is a contactor and an overload. If you go to page 16-30 in the digest, that's where we have what we call a combination starter. In that product, I mean, it's basic. What it is you get a overcurrent protection, either a breaker or a fuse switch, in line with the starter in a complete package. So instead of having to hang a safety switch on the wall and a starter on the wall, all you have to do is hang one device and you got everything included in one package. Any questions on that?
Well, that has a button in the whole motor.
That's where we put the pilot lights, you know, run, on, off, pilot lights, the handoff auto or the start, stop, push buttons, all that goes on the front of the enclosure. Right. And let's see. If you go to, where is it? Bear with me. I think that's way to the back of section 16. If you start on page like 16-117, kind of go back from there. There's all our different, you know, accessories and things like that that you can get with starters. In like 16-118 is where your start, stop, push buttons, your handoff autos, all that stuff are located. 16-119 is where your aux contacts for the starters are located. So, and these are the type of aux contacts that we would use for that holding circuit. Okay, so we really buzzed through starters really quick. Is there any questions I mean, we basically have two different types. We got manual or magnetic starters. You know, manual is just like it says, it's manually controlled, it's on or off. A magnetic starter, we use some type of separate control to control that starter. I did bring some information on like soft starts. If you guys heard that before, you might have to share because if you guys share, you know, two people.
We have it in the book here?
Well, we just have kind of a blurb. There's so many. This book is only 6 inches thick if we try to put everything in it, you know. But if we went back to where is it? No, you're okay. Actually, 25 is where the drives are located and soft starts. This is more open style. This brochure covers our enclosed products. So what a soft start is it just it's an electronic device that slowly ramps the motor up to speed and slowly ramps the motor back down to stop. Okay, and where we use that is in applications where a hard start, you know, full voltage start may be maybe a disadvantage, like pumping applications. If you try to start that pump up full speed, you get water hammer, which could cause pipes to burst. If you try and do it in an HVAC system, again, you get you overpressure the duct system and you can blow it apart. So what a soft start does is give it kind of a ramp up to full speed and a ramp back down. Once it gets up to full speed, you know, it kind of goes into it kind of switches or bypasses the electronics and lets it just run at full speed like it was on a starter. And then when you tell it to stop, then the electronics jump back in and actually decel that motor back down to 0. The difference between a soft start and a drive, the drive can actually control the speed of the motor. Okay, it'll do a ramp up, a ramp down, but you can also control the speed. In pumping applications, fan applications, stuff like that. And what we actually are doing with the drive, we're tricking the motor. I always think it's running at full speed. Have you guys heard of pulse width type drives?
Pulse width
Modulated?
No, hold on, I don't think
PWMs? Okay. When they first started trying to figure out how to control a motor, they first started, well, let's just vary the voltage. So all they did was vary the voltage, but they didn't vary the frequency. Okay, so all of a sudden they lower the voltage, the motor would decelerate, but they found out that over time the thing would burn up because, you know, so they actually decided to do the right thing, go back to the motor manufacturer and say, how do you design this motor? And they found out that motors are designed to a specific volts to hertz ratio. So at, you know, if it's 208 volts or it's at 460 volts, it's a 60 hertz. So then we started getting smart and going, okay, so now we have to start, when we reduce the voltage, we also have to reduce the frequency at that same amount, okay? So at half frequency or 30 hertz, we have to reduce the voltage by half. So in the beginning, we started using products like SCRs, you know, old technology, to, you know, try and vary the speed of this motor. And there was a bunch of issues with that. Number one, tons of harmonics. Number two, when you started getting down in the lower frequencies, you'd actually get what they call cogging, where the motor would start, you could actually see the motor jumping instead of a smooth rotation. So they right now we're using a product called an IGBT, isolated gate bipolar thyristor, and that product is very fast, switches on and off very fast. You can control it very fast. So now we can get much better control at any speed and get a lot of torque at the same time with that type of product. But what we're doing is, you know, you got this AC coming into the drive. We've got, and that, since this is, I'm not going to try and draw it, but we got a rectifier system, DC rectifier, full bridge. So it basically converts the AC to a DC voltage. Okay, and in the output, we have 6 IGBTs that convert it back into 3-phase AC. Well, actually, we are pumping DC voltage to an AC motor and thinking it's getting AC, and that's what this pulse width modulation means. Is we actually vary the pulse, the width of the pulse. So we may, and this is going to be really rough, I apologize. This is, it happens many more times than this, but this will kind of give you the gist of it. Then we do the same thing in the opposite direction, okay? So as you look at the different widths of these pulses, the RMS value, when you calculate it out, it all of a sudden starts to look kind of like an AC waveform. So the motor doesn't know any difference. It thinks it's seeing an AC waveform when we're actually pulsing UC to it. And this is how all the new technology works. So, and by varying the duration and the width of that upper pulse and lower pulse, now we are changing the frequency for, you know, to the motor, and at the same time we'll be reducing the amount of voltage. Whoops. So now we can control the motor at any speed, and it won't burn up. And I have pictures for that too. And these packages, again, the open style stuff is in the digest in section 25, but what you guys would probably be using on a project is our enclosed product. And the difference is, you know, this comes with, it's like a combination starter, only it's a drive or a soft start. It's got a disconnect, it's got the pilot lights, push buttons, all that stuff mounted in the enclosure. So all you have to do is hang it on the wall, hook it up to the motor, and away you go. Any questions on these products? Again, the soft start, all that does is a soft ramp up to speed and a soft ramp back to stop. Drive, we can soft ramp it, but then we can also control the speed of the motor at any frequency we want. So in a, why we do it in like fans or HVAC systems, I mean, they used to use a full voltage starter and run that motor at full speed and then use dampers, you know, to control how much volume actually gets through the ductwork. So that's like driving your car with the accelerator all the way to the floor and using your brake to control the speed. You're wasting tons of energy. Okay, so with the drive, we just control that motor to say how much air is going to flow through that ductwork, and by doing that, we save a ton of energy. So that's why people are using variable frequency drives a lot in pumping and fan applications, mainly to save power. What else was on the syllabus? That's motor control in general. We kind of covered the big items really quick. Panel boards, I think your project, right? Panel boards are in section 9 of the digest. We have 4 different types of panels. We have an NQ panel, which is on like 9-6 in the digest. And that's our 12208 type lighting panel, lighting appliance panel. The big change to these panels is in the last code revision, they took away the 42 circuit rule. Prior to the last code revision, we were always limited to a 42 circuit panel. They took that out of the code requirements. So now if you look on page 9-6, far left column, you'll see 7284 circuit panels. So what that helps us with is before, if we needed more than 42 circuits, all of a sudden we're looking at double tub panels, you know, where we have 2 panels. Now with this code change, we could probably serve all that with 1 panel now. So we're saving wall space, we're saving labor, and the cost is actually cheaper to use like 184 circuit panel versus 242. Okay.
So you guys are building 84.
We are building up to 84 circuit panel.
What is the NQ?
You know, I couldn't tell you. Our prior product was NQOD, and we did a design change, and the new product came out just NQ. So, but just remember, NQ is a 12208 volt product. Now, you know, I jump around, and you guys can yell at me if you want. And I'm racing again, Chad. I'm sorry. I can't control myself. But let's just talk about panel boards in general. Ooh, I like the word. Okay, they come in main lug only, MLO. So you just get lugs, or main breaker. Okay. And if you look in here, 9-6 is our main lug version, 9-7 is our main breaker. And I think this truck is leaking.
Is it? Oh, this picture.
Yeah, slam it. Okay, along with that, like when we talked about the double tub application or something like that.
Yeah, then somebody all equal for it. That's all equal. We did it.
We provide, there's different options. We got main lug and main breaker, okay? Then there's accessory, you know, like we call it sub-feed lugs, through feed lugs. Okay, so in that application where we used to use a double tub, and it was a main lug only panel, they come in, we would at this point provide sub-feed lugs, and what that does is it gives you a second set of lugs to go over. Wow, I really suck. Sorry. To feed a second panel, okay? That's sub-feed. Sorry. Through feed lugs is where we actually put the lugs on the opposite side of the panel. So it actually feeds through the panel and comes out the opposite direction. Where we use this a lot is at high rises, right? Where you got electrical rooms stacked up on top of each other, each floor. They'll come in the bottom of the panel and out the top to feed the next panel. You know, you just keep going. So that's feed through because we're feeding through that panel. You know, the lugs are on the opposite side. Sub-feed, the lugs are on the same side. It gets technical now. On main lug only panels, we can provide either sub-feed or through feed lugs. Okay. On main breakers, because the lugs are on the, you know, come basically whatever lugs are on the breaker is what lugs you get. On a main breaker, we do not offer the sub-feed lug option. It's through feed only to get the second panel. And there's different times when you can use a main lug only panel and different times when you have to use the main breaker, okay? If you have, like on your project, right, you got a main distribution panel, 500 amp, and it's feeding other panels downstream at 208, you can get away using a main lug only panel on those downstream devices, okay? If the service was 480 volt, and you're using a transformer to transform it down to 208, then at that point, that panel has to have a main overcurrent device. Because code requires, because you're deriving a new system. You're going from 480 to 208, and as soon as you derive a new system, you have to bond it. You got to treat it like a service, basically. So you have to provide a main breaker panel at that point. Okay. So the difference, you know, this is, again, NQ is our 208 option. And you're going to ask me the same question. I'm going to have to tell you I have no clue, but if on page like 9-13 is our 277 480 volt panel, which is our NF. And I'm sure that somebody has a reason why they call them these. I don't have a clue. So the NF panel is our 277 480 volt lighting appliance panel. And these panels, you know, you can get up to like a 125 amp max breaker, branch breaker in them. You know, it plugs onto the bus. I believe we have main breaker up to 600 amps and main lug up to 800. But we're still limited to the size of breaker we can put in the panel. So on your project, you know, you might have a couple 200 amp breakers or something on that in that panel, right? At that point, we would probably jump up to the next panel, which is our on page. Fingers don't work. 9-20 or 20 or 9-21. Sorry. And that's called our I-line panel or power distribution panel. Okay, you can use that at 208 or 480 volt, but it would normally be the main service type panel for your building. This panel can handle up to like 1200 amp branch mounted breakers, all the way down to 15 amp, but anything in between. Okay. So if you got a panel board that requires quite a few larger capacity breakers, you probably will be looking at an I-line panel as a service panel. We do offer, and again, I'm giving you my card, so if you guys got questions and want to know what type of panel would be best to use, call me. But on these NF and Q type panels, we do also offer what we call a sub-feed breaker. And what that is, you know, we got our interior in here that all the branch breakers plug onto. At that point, what we do is we put those feed-through lugs I was talking about in there, but then we actually mount a breaker separate in that enclosure and then cable it to those feed-throughs, and that can go up to like a 250 amp breaker. So if you only have one big breaker and the rest are all small, then Q might be a better fit depending on what your fault currents are and how many big breakers. Because this would be a lot cheaper than using that I-line distribution.
And that is an overcurrent protection device, that sub-feed breaker.
That sub-feed breaker is a breaker.
That's just a cover.
But it's mounted separately. It's not attached to the bus. It's cabled to, but it's mounted in the panel. So there'll be a cutout in the panel where that breaker is located so you can operate the handle. But that's how we can put at least maybe one or two of those larger breakers. Okay. And there's cutoffs, and again, call me, because like on a 250 amp or smaller, we can put 1 sub-feed in. Just 400 amps or bigger, we can put 2 in. And it all has to do with the lugs for the feed through, right? Because at 400 amps, those feed through lugs are rated for 2 cables per phase. So now we can sub-feed 2, where at 250 amp, those lugs are only rated for a single cable, and that's why we can only do 1.
You prefer email or phone?
Either probably phone or email's better, because
Right.
I'm here today and I'm running like crazy, so in meetings. So sometimes when you call me, you'll have to leave a message. If you shoot an email to me, I got it right now. I can look at it if I have time. But I like to talk to people too, so either way. So this is kind of a disaster here. Do you want to really keep that?
You can push the button, green button right up, and you can just.
Okay, here we go. So in your project, we have a utility, a generator, right? And you are feeding that into an ATS, automatic transfer switch. Okay. Now, on automatic transfer switches, there's a ton of different options as well. Actually, we don't make them anymore. We got out of the market, but I know enough to be dangerous, okay? So there's all sorts of options. You got open transition, closed transition. Hey, I'm getting better. You can almost read my writing now. So obviously it's pretty self-explanatory. You know, an open transition, you know, if you lose your utility, you go to gen power. Obviously that's open anyway because you already lost the power. The transfer switch will send a signal to the generator. Generator will start up. Once the generator is up to speed frequency, the transfer switch will close to the generator power, provide power. Okay. Now it's when the utility comes back that's where this difference comes in, right? Because all of a sudden the ATS senses that the utility's back. An open transition, it will actually disconnect the generator and then connect to utility, so you get a blip in there, a loss of power on the retransfer as well. Okay, on a closed transition, for just a few cycles, right? It will wait until that utility and the generator are synchronized. Okay, in other words, they're on the same. The waveforms are exactly the same. When that happens, it'll close in the utility. So now your utility and gen are tied together for just a little bit. Once that happens, it'll take the generator offline. So at least on the retransfer back, when the utility power comes back, you won't have a second blip. Okay. Now there's 3-pole and 4-pole ATS. 3-pole switches the phase, you know, the ABC phase power, but does not switch the neutral. Okay. A 4-pole switches ABC and neutral. And where you have to use one versus the other, say, well, in this application, since this is utility, you probably have to use the 4-pole transfer switch because they're probably going to bond this generator to ground. I mean, you always ground a generator, but they'll probably bond the neutral to ground, and that's the service entrance, right? So now they'll treat this like a service entrance. So it's deriving its own ground reference. And the utility is bonded. So now you have the potential of neutral currents flowing either direction, either to the generator or to the utility. So in that application, we would use a 4-pole device so that the neutral phase currents are all switched back and forth to each source, okay? Now say that instead of a utility here, you know, utilities upstream. Oh, what did I do? It's not writing them. You know, we're feeding a main switchboard. We're bonding this at this location, right? Neutral to ground because it's the service entrance. Well, instead of bonding the generator here, we can actually run the ground for the system, right? You still have to ground that generator, but that's the enclosure ground, right? That's the equipment ground. But the actual ground from the generator, you know, the power it's deriving, you can run that back to the same ground point as a service. So now the bond is still here. This isn't bonded over here. Well, at that point, you have the same ground location. So all your neutral currents, no matter which device is running, is going to flow to this point. In that application, you can use a 3-pole. Okay. And it's up to the engineer. I've seen them go both ways, where they bond this or they bring it back to here. Even the generator guys aren't always sure when they use a 3 or a 4-pole transfer switch. It gets kind of confusing, but that's the difference. Okay, if they bond the generator, if you know they're going to bond that generator as a service entrance, then you have to use a 4-pole break or a transfer switch. In your other example, where we were feeding right from the utility to the transfer switch, not only do you need a 4-pole, but then you also need a service entrance rated transfer switch. So basically built into that transfer switch is going to be overcurrent, you know, a breaker or a switch or something. Normally breaker, right? Upstream, internal. Can't even write. Yeah. Anyway, so this is where now that utility service will be bonded inside this enclosure, right? Yes. Yeah. It really depends on the ampacity of it, but it's probably 15%, 20% more. As you get into the bigger ones, it gets much larger than that, but in the smaller ones, it's not as big a percentage change.
About the difference in price between the both
that is probably a significant change, right? Because on a closed transition, we need a sync check relay where we're feeding voltage from both sources, and the relay itself is checking when they come into sync, and at that point it'll start doing the transfer. It requires more control and more, you know, like protective relays and stuff like that. So it is more expensive.
Where are you seeing them?
Closed transition, data centers, hospitals, you know, somewhere where that second flip is not industrial processes. You know, certain industrial process like a glass plant, you lose power. It could screw up hundreds and hundreds of feet of glass where they're just busting it out and cleaning up machines and before they can even start up again. So banks, maybe, you know, if it's a run-of-the-mill school or mall or, you know. So what if you guys are in the dark for a while? You know, who cares? You know, it's just the application, right? Yeah. I think that kind of covers it for transfer switches. I'm pretty sure. Now, obviously, off of that, we're going to feed your main distribution panel. And again, depending what all your loads are, because at this point, I don't know if you know what your loads are in those panels. If it's got maybe one large breaker, 200 amps, you know, something like that, and the rest are 100 amps and less, you know, we may make that an NQ, or we may make that an I-line panel. And that reminds me. Sorry, it was over on in my trunk yesterday. So this brochure kind of covers our I-line panel boards and our switchboards, okay? Because Chad wanted me to cover switchboards as well. If you look inside, you know, a standard breaker for an NQ panel, you know, it's a small breaker. The breakers that go into this I-line distribution panel are huge. They're molded case breakers, and they're probably, you know, 100 amp breakers probably and smaller. Even a 50 amp breaker is probably about this big. A 1200 amp breaker that goes in there is, you know, 15 inches tall by at least 17 inches wide. So we're talking much bigger devices in a distribution panel. There's also, you know, your short circuit current rating could dictate which panel we use, because you know, I should have back to this. That's something I did not cover. There's fully rated panels. Have you guys heard of series rated panels? Okay, and these NQ panels, which is our 208, we can fully rate up to 22,000 amps of fault current, okay? But we can series rate it up to 65, even higher, depending on what the, and what we're actually doing a series rating is the main breaker net panel, or at least the breaker that's upstream that's feeding that panel. We've actually tested the combination of that breaker and these breakers that are in this panel board, right? Like QO breakers are rated for 10K. Well, we actually have series ratings depending on what the main breaker upstream is that are good up to 65K, because that main device is rated for 65K. These breakers are rated 10K, and we actually shoot that combination of 65,000 amps of fault current. And what happens is that main reacts much faster than the smaller branch breakers. And by the time these branch breakers start to act, the main's pretty much taken out most of that arc from the fault, so that we don't have things exploding within the panel board, okay? And we have to do that with all that testing for these combinations with UL. And if, you know, if the breaker burns, or if a wire falls off, or anything like that because it stresses the fault current, we fail the test. And we someday, I mean, I don't know how we would do it, but Cedar Rapids, Iowa is where our test lab is. It's kind of fun to go down there sometimes and watch them blow shit up. I mean, they can generate up to, I think it's 300,000 amp fault current in that facility. And it's not as much fun to watch a panel board, but some of these bigger products, we have to test, you know, our switchboards and our switchgear. You can actually start seeing the phase buses moving because of the fault stresses within it under a fault condition. So fully rated means everything in that panel is rated for the available fault current. Series rated means it's a tested combination. Probably the main's rated for the fault current, but the branches aren't. And again, if you have a fault with the series rated panel, it's a good chance you're going to lose the whole panel, because the main's going to take the fault out. Okay. On a fully rated panel, Still could. I mean, still could take the whole, but you got a better chance at least maybe that 20 amp breaker that's feeding that outlet where the fault occurred, tripping and not losing the whole panel, but just that circuit, right? So, hospitals, data centers, you probably don't want to look at series rated product, right? You want to look at fully rated, but schools, malls, you know, stuff like that, this is probably a good place to look for, you know, series ratings because it's going to save you a ton of money. So that's series rated and fully rated. And I didn't tell you that, but at the very beginning of section 9, and I think it starts at 9-2 and kind of goes back, are all the series rating combinations we have for our NQ, NF, and island panel. Okay, so for this for your project, at this point, I'm just going to assume we're going to use an island panel, 500 amp, right? Now we're going to feed down to 2 other panels that are probably
There's 200 and 100.
okay. So these are probably NQ panels, okay? Or load center. I don't know what you want for. I mean, the difference. I don't think you'd want to use a load center in a commercial project, but some people do. 3-phase load centers. The difference between load center and a panel, you know, the load center is a device in your house, right? And then you got the little house you open up. It's probably rated for 22K. But a load center is really designed for residential applications. It doesn't come with a locking hasp. It's much smaller airspace within it, okay, because normally residential doesn't have a lot of load demand on it. Okay, panel boards, you automatically get the locking door hasp. The panel's going to be physically bigger because it's got more airspace within it, for more wireway area, more heat dissipation, you know, things that you would probably run into a commercial application. Okay, so I would probably say these are NQ. Oh, what did I do? Okay. Now this eyeline distribution panels, we can go up to 1200 amp with that. But let's say your service was a 2000 amp service. Okay, now all of a sudden, in that same brochure I handed out, the first page kind of is their panel boards. It's wall mounted, right? Because it's only 9.5 inches deep, so you have to attach it to the wall, and it can go up to 1200 amps with a 1200 amp max branch breaker. On the very back of it, not the very back, but the last page, this is our switchboard product. The interiors use the same breakers as we do in the eyeline panel, but we can go up to 4,000 amps with this product. The interiors are much bigger, so we can fit more breakers. You know, if you did have, you know, like a 3,000 amp main and a 1,600 amp branch device, well, we can do that with a switchboard. We'd have to provide an individually mounted breaker. It would be in its own enclosure, 36 wide, but we could put a 1,600 amp in there to feed that large source. So panel board, 1,200 amp max, 1,200 amp max breaker. Switchboard, minimum 24 deep. So now we're talking a freestanding device. It doesn't have to be attached to the wall. It sits on a concrete slab. And as we get bigger in ampacity, they start getting deeper. So 2,500 amps and below is 24 deep. 3000 is 36 deep, 4000 is 48 inches deep. And really, from the outside, you wouldn't know the difference between them because they don't all pretty much look the same. Depth is different. We have different interior options with it. But is there any questions? I mean, like I said, I'm covering really fast because I only have maybe an hour and a half to cover this stuff. But when you get into your next project, I'm assuming the service house is going to be bigger, right? 4,000 amp service. So you'll probably be looking at a product like this. And I can help you guys out with dimensions and stuff like that. We don't do Revit yet. We came out with Revit drawings initially, but we basically used our manufacturing drawings like everybody else in the market did. Well, they're 5, 10 meg, because it's got all the internal details in it as well. So we are in the process of dumbing that drawing down to get it something at least a case, right? So it's usable, because as soon as you put a 5 or 10 meg file in that Revit thing, you just stopped it. It slowed the system down phenomenally. So I'm hoping by the end of the year we may have that finished for our switchboards and some of our products. We do have Revit for more generic safety switches, transformers, stuff like that. I think if you go to Schneider-electric.com, there's a drawings. I think there's a 3D file
Which you can download
you can download.
as a family.
Right.
Into the project.
Correct. But the big equipment like this that's engineered to order, we call it, because every time it's different, every time we engineer it specifically for the project, it's built specifically. We're not to that point. But I can get you 2D drawings that you can possibly convert into a 3D, at least know the dimensions of it. So if you need that, tell me what your service looks like and what you have inside of it. I can send you the front elevation, the footprints and stuff like that to at least help you get that dimensions. Okay. Again, this product is what we call switchboard construction, and this UL 891 is a UL listing for that product, and basically it's group mounted. And we call it group mounted because if you look at that last page, all the breakers are pretty much grouped together. They're sitting side by side. The main's in its own enclosure normally, but all the distributions side by side. There's no barriers. You know, if you open up the front cover, you'll be able to see the breaker terminals, and way back farther, you'll be able to see the main bus. Everything's pretty much new. Okay. We use this on commercial projects. You know, you can use it on hospitals and stuff like that, depending on the application. We also have a product which is Switchgear.
You sell strictly for distribution, or?
Correct. Well, I have to take that back. We do have some accounts that are direct accounts. That buy directly from us, but they've got to be very large and they just use them because, you know, us as a company really support our distributors. And they're the ones that bring the product to the local market, right? Stock it, everything else. So we try and run as much as we can for distribution. Now, this is Switchgear, okay? Serves the same purpose as the switchboard, but this has a different UL. This is 1558. And the difference with this product is, if you go kind of open up that front screen, it's really hard to tell, but on a switchboard, most of the terminations are available from the front. You know, so we can build it from access only, so you can slide it against the wall and still get to all the terminations and stuff like that within the product. Switchgear is built so everything's buried from each other. You know, the breaker compartment is the very front, which is buried off in the bus compartment, which is in the middle. And we provide barriers as an option to barrier the bus and cable compartment from each other. So each area is barriered from another. And we actually put side barriers in, so each section where you're making these cable connections is barriered from the adjacent system. That's number one. So as you look, the breakers in the front, all the terminations in back. So draw a switchgear like this requires front and rear access. You can't put it against the wall. You have to have it off the wall. Where they use this product mainly is in the data center. They may use it in hospitals for certain applications. It's where you need, like in a data center, if a breaker goes down, they want to replace that thing right now. So in switchgear, these are what we call draw breakers. They're not, like the other breakers that are attached to the bus. There's a cell inside here, if I find it, like on the inside of this cover, right? You can actually do a crank, and you can crank this breaker out, and once it's cranked out, you can just pull it. And you normally have like an overhead lifter frame that rolls across the top. If you go down, you grab the breaker, you pick it up, you put it on a tray, they wheel it away. They normally have a spare for the data center. They bring the spare in, they roll it up, they put it back in the tracks, and then rack it in, so you can replace the breaker in minutes. Okay. Switchboards, not that easy. You have to tear dead fronts off and all this stuff to get, to physically remove the breaker. This equipment also, the big difference is, it has to withstand the fault current for 30 cycles or half a second. So if you have 100,000 amps of fault current available, it's got to be able to take that fault current, that 100,000 amps, for at least a half a second before it goes offline. Switchboards are what we call AIC rated, amps interrupting capability. They may be able to take that 65K, but the breaker's going to take that fault off within cycles, a couple cycles. Switchgear is designed to wait. You can set the breaker up to wait up to 30 cycles. So why is that important? For coordination. So you can coordinate with the downstream devices, because you want that main gear to sit there and hold that fault for as long as you possibly can to allow that downstream device that's closer to the fault to take that fault out. And that's where we start using this type of gear, is hospitals on emergency systems, data centers, something where it's that. Have you talked to them about the selective coordination requirements in the code?
A little bit, but
Okay.
we're doing it.
Well, when you get to that point, let me know, and I can send you information. But the code requires.
Well, let's move them off.
Oh. The code requires an emergency system of a building to be what they call selectively coordinated. The definition of selective coordination is the device closest to the fault has to take that fault out. So to us, that means fully coordinated. Every device in that system has to be coordinated. So if you're looking at a TCC curve, time current characteristic curve, every breaker has a trip curve. And you guys are going to use SKM if you haven't already.
Mm-hmm.
Yeah.
That's good.
So all of a sudden you start picking breakers, and that 20 amp breaker may have a trip curve that looks like this. Now you got a 400 amp main breaker in that panel.
Use different colors.
Okay. So all of a sudden that 400 amp breaker has a curve that might look like that. If we're talking strictly like a thermal mag breaker, where A thermal mag breaker uses a bimetal and a magnet internal. So the bimetal, as your current goes up, that bimetal starts deflecting, and when it gets to a certain point, it trips the handle mechanism and the breaker trips. Okay. Magnetic, it's like a coil with a plunger, and when the fault comes, bang, it takes that breaker offline right away. So in this particular application, at that point, whatever it is, we've lost coordination because we can't tell which breaker at this point is going to trip because they're overlapping. Well, selective coordination says, you know, that's not acceptable. Unless, you know, you do say this point is 4,000 amps, you know, and you're on the secondary side of a 75 kVA transformer, something that can only provide 33 amps, so all of a sudden your available fault currents here, and where you lose coordination is there, you're coordinated at that point, okay? Now, in the hospital, we're probably talking much bigger fault currents than that, so now we'll start looking at solid state breakers, which is a microprocessor based breaker that has CTs internal to it and a trip unit that you can actually have potentiometers that to adjust the trip curve on the breaker. So now all of a sudden this solid state breaker, 400 amp, you know, we can adjust long time. So if it's a 400 amp breaker, we can dial it down to 0.4. So we can dial it down to 160 amp breaker up to 400 amps. And then there's the short time portion of that breaker. And the short time is like anywhere to from 2 times the handle rating of the breaker to 6 times the handle rating of the breaker. And we call it the short time because it kind of covers the mid portion of the curve, and we can adjust this part of the curve up. Oh, wait, I suck at this again. Or we can adjust it this way. So now we have full control of that curve. We can move it this way, we can move it up and down, we can move it left and right. And then on our larger solid state breakers, we have the ability to turn off the instantaneous. So, but even if we turn off the instantaneous, there's still what they call a selective override built into every breaker, and that's the amount of fault current that breaker could probably withstand without blowing off the wall. Okay, and that might be 18,000 amps, it might be 65,000 amps, depending on the type of breaker and the design, right? So all of a sudden we turn off the instantaneous, and we are all of a sudden moving this curve way the heck over here to whatever that override on the breaker is, you know, on our frame that's 35K. So now all of a sudden that 400 amp breaker, we're fully coordinated with that downstream breaker. Now you got maybe a service breaker that's rated at 2,000 amps. We use that same type of breaker, you know, solid state breaker, you know, but it's way over here. And we just adjust it to make sure, you know, that its curve doesn't overlap with the one in front of it. And you're still going to get a tail, you know, on the solid state breakers. But it was anything above this point, that breaker is going to trip. And anywhere above this point, that breaker is going to trip. But now, at least we're coordinated to, you know, wherever this is, which might be 56K or 65K or whatever the override is built into that breaker by turning the instantaneous on. Does that make sense? So this is what we get to deal with on hospital jobs every day of the week is before we even bid the job, we have to do some type of a quick study to make sure we pick the right breakers that are going to coordinate, well, at least what we think is going to coordinate. But we won't know for sure until probably towards the end of the job when we actually do a full-blown short circuit study, so we know what the fault currents are at each of these buses, And then at that point, we can do a full coordination study to pick the right breakers. But we do our best to get it coordinated up front, so there isn't big change orders and stuff at the backside. So that switchgear, the breakers we use in that switchgear, those NWs that can handle that fault current for 30,000 or 30 cycles and stuff like that, their overrides are way over on this side. You know, 656, 65, 85K, where the breakers we use in switchboards are probably down in this 38, 20, you know. So based on that, that may dictate us to use the switchgear versus switchboards, at least at the service entrance area. So like I said, hospitals, data centers, you know, any application where down power, you know, being down is bad, we start looking at maybe using this type of product at the service. I blew through this really fast. Okay. Any questions?
You find many instances where you have dual power?
Two utilities?
Well, they get it from two different spots, so
Right.
basically the business would react to commercials, and they lost power one time and they spent $5 million on advertising, nobody's there to answer the phone,
Right.
so they have a problem.
U of M has multiple sources. Fairview Hospital, Riverside, we just put in a 13,800 volt system that they're feeding two utilities into. So, and we have, I didn't really cover that either, but I just did that. We have the ability to pull in two utilities. So this distribution is fed from that main, distribution is fed from that main, and then we have a tie breaker in the middle that ties the systems together. It can be manual, or we can do it as an auto throwover system using PLCs to control the breakers. So obviously if you use Kirk keys or key interlocks, it's a manual system, so if you lose the power to this source, what you do is you open the main up. Once you do that, it allows you to pull the key out, put it into the tie, and that allows you to close the tie, so now you're feeding the power for both sides from that main, or vice versa. And then when you have both sources, you open the tie, you close the main, and now they act as separate entities. We can do it with, like I said, what we call an auto throwover system. Actually mount PLCs and relays. We can do the same thing as transfer switches like that. We can do open transition, we can do closed transition. We can provide 3-pole breakers, or we could provide 4-pole breakers. Because whenever you have a system like this, right, you still have your ground and your neutral bus tied together. The tie isn't necessarily switching that, right, with the 3-pole breaker. So now, all of a sudden you have a ground fault. Well, what happens is now the power, instead of coming back on the neutral, the switchboard, right, from that source, it's going to ground. So, say that was an 800 amp breaker. Well, now you got 800 amps of neutral current that should be coming back on the neutral, flowing to ground. And that's how a ground fault system works, because we read what's going on the phases, what's coming back on the neutral for, you know, that main, and if 3,000 amps going back and only 2,200 amps, or 3,000 amps going out, only 2,200 amps is coming back, we know we have 800 amps of ground fault current flowing in the system. So we can either use integral ground fault protection on that main or a separate relay, but either way, they kind of work the same. You set it up so at 800 amps, so you set up the current and the delay, and you say, okay, 800 amps at 0.3 seconds. So if it's seeing it's missing 800 amps, it'll wait 0.3 of a second, but it'll blow that main. What happens is, you know, we got 2,200 amps of neutral current still flowing, but we're tied to both services because we're not breaking that neutral. So now you got 2,200 amps of current flowing. If it's identical system, the impedances are identical, everything, you'll have 1,100 amps flowing to this main, and 1,100 amps flowing back to this main. Okay. Now all of a sudden, or even if you don't have a ground fault, let's say you don't have a ground fault, you have 3,000 amps of fault neutral current coming back. Without switching that, now you got.
I was just looking for a yes.
Yeah. Yes. How's that? They get 1,500 amps flowing both directions. Well, the system's automatically going to assume you have a ground fault at that point and trip. So we have to design a special ground fault system to accommodate for the neutral currents flowing both directions. Okay.
Jerry, do you guys do this at low voltage, 480 or?
This is 480. We do it at 1380. We do it at any voltage. Now, it makes it easier, right? Because that ground fault system could be very expensive depending on how many relays and all that stuff we have to add to the system to be able to account for neutral currents flowing back to both services. If we use 4-pole breakers at each of those locations, now we're switching the neutral as well to both sources, and we don't have to worry about that funky ground fault system because now the neutral current can only flow either to that main or back to this main. And when you disconnect the tie, now you break that neutral, so whatever current's flowing here is going to go that way, and whatever current's flowing here is flowing that way. So, they overkill, but yes. What's that? We get even more complicated than that because we can start looking at not only 2 utilities but 2 gens feeding to the same, and start doing transfer schemes for that as well.
Any questions, guys? Any comments?
Have I bored the SIG audio? Anyone? Again, you'll have my card. If you have questions when you're working on your projects, feel free to give me a call. If you want to email me one-lines or whatever, you know, I can start helping you do dimensionals, right, on the different items.
Who's your largest local distributor?
We have 2, Graybar and Border States, and they're kind of the same size. And then we have a bunch of others that are smaller, but niche markets. So.
Any comments or questions for Jerry? Jerry calls on all the consulting engineers in town. He's still doing that.
Yep.
I see him around when you get hired on Hallberg and all those guys. You still go to Hallberg every week?
Not every week. Like right
The
now,
donuts?
I do Nashad every week.
I mean the shot.
Yeah, I'm at Nashad every week, and I'm at Dunham every other week, and I'm on HGA every other week. Mainly because those are the firms that allow me to do it. You know, it's kind of hard to get an engineering firm to allow a vendor to come in and sit and look at people come up and talk to them, because billable hours is what they do, but they found benefit in it, so I take advantage of it. But yeah, I pretty much cover all the consultants, and I do have 3 electrical contractors now, because of downside, people retiring and not replacing them, so I still got my hands in the electrical group. ERC must comment. So, nice to meet you. Yell if you need any help. I'm going to leave all this literature. You got it?
Yeah. Thank you, Jerry.
Oh, you know what? I didn't cover it, but I'll just hand it out. This is called our integrated product. And basically what it is we start putting panel boards and transformers and things like that in the same enclosures. So instead of having to mount a 480, 277 volt panel board, a transformer, and a 2-way panel that might take up, 6 or 8 feet of wall space, we'll mount them all in one enclosure. It's 42 wide, 24 deep, and so now all you have is one device to set. You take up less room, you save a ton of labor. It is more expensive than stick built, but in our market, where you're paying $70+ an hour for labor, it actually makes a lot of sense. So, and I'm gonna leave these.
Yeah,
I gave you one.
Okay, thank you. I appreciate it.
And this is just one example of it. We have sections, we'll put 6 panels in one section.
No.